On the morning of April 1st, 1945, Lieutenant Commander Malcolm Cagle stood on the flight deck of the USS Hancock, watching his ordnance crew struggle with what looked like a telephone pole strapped beneath a Corsair fighter. The weapon measured 11.75 inches across and stretched nearly 10 feet long, weighing in at 1,300 pounds. The Japanese had never seen anything like it. More importantly, they had no defense against it. This was the Tiny Tim rocket, and this morning it would be paired with something even more revolutionary: radar guidance that could find targets through clouds, smoke, and the chaos of battle. The Japanese Navy had built their defensive doctrine around visual spotting and manual anti-aircraft fire. That doctrine was about to become obsolete. The Pacific War in 1945 had reached a critical phase. American forces were closing on the Japanese home islands, but each mile cost blood. At Iwo Jima, which had fallen just weeks earlier, nearly 7,000 Americans died, taking an island 8 square miles in size. Okinawa, the next target, would be worse. The Japanese had learned that they couldn't win conventional engagements anymore, so they adapted. They hid their ships in harbors protected by mountains. They positioned artillery in caves that American spotters couldn't see. They launched kamikaze attacks under cover of weather that grounded American fighters. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The American response required a weapon that could reach targets regardless of visibility, terrain, or weather. It needed the punch of a bomb but the speed of a rocket. And it needed to be accurate enough to justify its massive cost in materials and engineering hours. The Tiny Tim rocket had been designed to provide the punch, but accuracy had remained a problem until someone suggested pairing it with the new generation of airborne radar systems that had been developed for night fighters and patrol bombers. The idea seemed straightforward on paper. Mount a radar set in the nose of a fighter bomber, use it to locate targets through any weather, then release a massive rocket that could penetrate ship armor or collapse bridge structures. In practice, every element of this system pushed the boundaries of what 1940s technology could achieve. The radar units were temperamental, requiring constant calibration. The rockets themselves were barely stable in flight, and the aircraft carrying them had to withstand the violent recoil of launching what amounted to a small missile from under their wings. To understand why this weapon system represented such a leap, you need to understand what came before it. American naval aviation in the Pacific had relied primarily on dive bombing and torpedo attacks. Dive bombing required clear weather and exposed the attacking aircraft to concentrated anti-aircraft fire during the final approach. Torpedo attacks worked well against ships in open water, but were nearly useless against vessels anchored in protected harbors. Both methods depended on visual identification of the target, which meant Japanese forces could simply wait for bad weather to move supplies, reposition ships, or launch their own attacks. The Tiny Tim rocket had been conceived back in 1943 at the California Institute of Technology, where a team of engineers led by Charles Lauritsen was exploring ways to give aircraft the firepower of naval guns. The name itself was ironic, a piece of American humor naming the largest air-to-surface rocket in the inventory after a diminutive comic strip character. The rocket carried a 500-pound semi-armor-piercing warhead, the same type used in 1,000-pound bombs. The propellant grain burned for just under 1 second, but that was enough to accelerate the weapon to 550 miles per hour. Early tests of the Tiny Tim revealed both its potential and its problems. When the rocket worked, it was devastating. Test shots against surplus destroyer hulls punched completely through the ships, entering one side and exiting the other before detonating underwater. Against concrete bunkers, the weapon could penetrate 6 feet of reinforced construction. The problem was consistency. The rocket's sheer size created aerodynamic instabilities that made accurate aiming nearly impossible. Pilots reported that launching a tiny TIM felt like someone had grabbed their aircraft by the tail and shaken it. The recoil could throw a fighter off course by several degrees, and at the distances involved, a few degrees meant missing the target by hundreds of feet. Engineers tried multiple solutions. They experimented with different fin designs. They adjusted the propellant mixture to change the burn rate. They modified the launching rails to ensure cleaner separation from the aircraft. Each change helped incrementally, but the fundamental problem remained. The rocket was simply too large and too powerful to be fired with the kind of precision that aerial warfare demanded. A pilot had to point his entire aircraft at the target, account for the rocket's drop and drift, release it at exactly the right moment, and hope that nothing went wrong during the brief but violent launch sequence. By late 1944, tiny TIM rockets were in service but rarely used. Pilots preferred more reliable weapons. The rocket's poor accuracy meant that it was only deployed against targets large enough and important enough to justify expending such an expensive and temperamental weapon. Bridges occasionally qualified. Large ships in open water qualified. But most of the time, conventional bombs did the job with less drama and more predictability. Then, someone in the Navy's Bureau of Aeronautics had an idea that seemed almost absurd. What if you could guide the rocket after launch? Not with the rocket itself, but with the aircraft's targeting systems. The technology existed. American night fighters were using airborne radar to find and engage Japanese aircraft in complete darkness. Patrol bombers were using similar systems to locate submarines on the surface at night. The radar sets were being miniaturized and refined constantly. Could you put one in a fighter bomber, use it to find a target through weather or smoke, and then use that same radar to aim a tiny TIM rocket? The concept required solving several technical challenges simultaneously. First, the radar needed to be small enough and light enough to fit in a single-engine fighter without compromising the aircraft's performance. Second, the radar display had to be integrated into the pilot's instrument panel in a way that allowed him to fly the aircraft, read the radar, and manage the weapons system all at once. Third, the launch sequence had to be coordinated with the radar lock so that the rocket was fired at the precise moment when the radar indicated the geometry was correct for a hit. A team at the Naval Air Station in Patuxent River, Maryland, began working on the problem in December of 1944. They started with the F-4U Corsair, which had already been modified to carry tiny TIM rockets on external hardpoints. The Corsair was a good platform for the experiment because it was fast, sturdy, and had enough internal volume to accommodate additional equipment. The radar unit they selected was a modified version of the APS-4 search radar, which had been designed for night fighters but could be adapted for air-to-surface work. The first challenge was power. The radar required a substantial electrical supply, and the Corsair's generators were already running at capacity with the aircraft's existing systems. Engineers had to install an additional generator driven by a small wind turbine mounted under the fuselage. This created drag and reduced the aircraft's top speed, but it provided the necessary power for the radar system to operate continuously during a mission. The second challenge was cooling. Radar sets generated significant heat, and in the cramped confines of a fighter aircraft, that heat had to be managed, or it would damage the equipment and potentially endanger the pilot. The team designed a dedicated cooling system that used ram air from the aircraft's forward motion to keep the radar components within operating temperature. This worked well at high speeds, but meant the system could overheat if the pilot had to loiter at low speeds for extended periods. The third challenge was the display itself. Early airborne radar systems used cathode ray tubes that were difficult to read in bright sunlight and required the pilot to look down at an instrument panel while flying at low altitude over hostile territory. The Patuxent River team developed a simplified display that showed only the essential information: target range, bearing, and a firing solution indicator that lit up when the aircraft was in position to launch. This allowed the pilot to make quick glances at the radar without losing situational awareness. By February of 1945, they had a working prototype. The modified Corsair, designated F4U1DR for radar equipment, underwent flight testing at Patuxent River and then at the Naval Air Weapons Station China Lake in California. Test pilots reported that the system worked but required intense concentration. The pilot had to manage throttle, altitude, and heading, while simultaneously monitoring the radar display and waiting for the optimal launch window. It was demanding work, and it became clear that only the most experienced pilots would be able to use the system effectively in combat. The Navy selected a small group of pilots from squadrons that were already experienced with the Tiny Tim rocket. These men had dozens of combat missions in the Pacific and had volunteered for what they knew would be experimental and potentially dangerous work. They spent 3 weeks training with the radar-guided system, learning to interpret the display under various conditions and practicing launches against mock targets in the California desert. Lieutenant Commander Cagle was one of these pilots. He had flown from the USS Hancock since the carrier arrived in the Pacific Theater in late 1944. He had participated in strikes against Formosa, the Philippines, and the Japanese home islands. He had dropped conventional bombs, fired rockets, and strafed ground targets, but he had never used anything like the radar-guided Tiny Tim system. In his post-war memoirs, he described the training as both exhilarating and humbling. The radar gave him capabilities that no fighter pilot had ever possessed, but it also demanded a level of multitasking that pushed even experienced aviators to their limits. The system was declared operational in late March of 1945. By that time, American forces were in the midst of the Okinawa campaign, which had begun on April 1st with the largest amphibious assault of the Pacific War. The Japanese response was fierce and immediate. Kamikaze attacks intensified, with hundreds of suicide aircraft targeting the American fleet. The Japanese also kept their remaining conventional naval forces hidden in harbors along the Okinawan coast and in the nearby islands, waiting for opportunities to strike. Intelligence reports indicated that several Japanese destroyers and cargo ships were sheltering in Naha Harbor on Okinawa's western coast. The harbor was protected by steep hills on 3 sides, making conventional dive bombing difficult. The ships were also defended by concentrated anti-aircraft batteries positioned on the surrounding heights. Previous American attacks had been costly, with several aircraft lost to anti-aircraft fire without achieving decisive results. The radar-guided Tiny Tim system offered a potential solution: strike from a distance, through weather if necessary, before the Japanese gunners could establish effective firing solutions. Cagle's mission briefing on the morning of April 1st was straightforward in concept but complex in execution. He would lead a flight of 4 Corsairs, 2 equipped with the radar-guided Tiny Tim system, and 2 flying as escorts with conventional armament. The strike would take place at dawn, when morning mist and low clouds over Okinawa would provide cover from Japanese fighters and make it difficult for anti-aircraft crews to track incoming aircraft visually. The radar would penetrate the weather, locate the ships in the harbor, and provide the firing solution for the Tiny Tim rockets. The plan assumed that everything would work as advertised. The radar would function properly despite the humidity and temperature variations of tropical operations. The rockets would separate cleanly from the aircraft despite the added weight of the radar equipment. The pilots would be able to locate, identify, and engage targets while flying through clouds at 300 miles per hour just a few hundred feet above the water, and the Japanese would not have time to react before the rockets struck. At 0530 hours, Kegle's flight launched from the Hancock. The carrier was operating approximately 60 miles east of Okinawa, close enough to minimize flight time, but far enough to avoid the kamikaze aircraft that were targeting the fleet with increasing desperation. The four corsairs formed up in the pre-dawn darkness, their navigation lights dimmed to the minimum visibility. Kegle checked his radar system during the climb-out, confirming that all indicators showed green and the display was functioning properly. The flight took 30 minutes, flying low over the water to avoid Japanese radar detection. As they approached Okinawa's western coast, the sun was just beginning to rise behind them, but the target area remained shrouded in mist and low clouds. Under normal circumstances, this would have meant aborting the mission or waiting for the weather to clear. But the radar changed that calculation. Kegle could see the coastline on his display, a bright line showing the transition from water to land. Beyond it, the harbor appeared as a dark area surrounded by the bright returns of the hills. And there, inside the harbor, were 6 distinct contacts. The radar couldn't tell him what kind of ships they were, but the size and positioning of the returns suggested something significant. 3 of the contacts were clustered together near the harbor's northern end, while 3 more were spaced along the western shore. Kegle made a quick decision. He would target the northern cluster with his radar-guided Tiny Tim, while his wingman, also equipped with the system, would engage one of the ships along the western shore. The attack run required precise coordination of speed, altitude, and heading. Kegle descended to 500 feet, well below the cloud deck, but high enough to give the rocket's trajectory clearance over the harbor's surrounding terrain. He adjusted his heading to align with the strongest radar return in the northern cluster, a contact that his radar indicated was approximately 400 feet long. That suggested a destroyer, or possibly a large cargo vessel. The firing solution indicator on his display began to flicker as the geometry approached optimal. Kegle made small corrections with his stick, keeping the aircraft stable despite the turbulence caused by the early morning thermal conditions. His thumb rested on the rocket release button, waiting for the solid green light that would indicate the precise moment to fire. At a range of 2,000 yards, the indicator went solid green. Kegle pressed the release button. The Tiny Tim rocket separated from its hard point beneath the Corsair's right wing with a violent shudder that jolted the entire aircraft. For 1 second, the rocket's motor burned, accelerating the 1,300-pound weapon toward its target at a rate that no human eye could follow in the hazy conditions. Kegle felt the aircraft lurch as the rocket's weight disappeared, and he immediately applied the opposite rudder to compensate for the sudden asymmetry. He couldn't see the impact. The mist and clouds obscured the harbor completely from his position, but the radar told him everything he needed to know. The bright return that had indicated the target ship suddenly fragmented into multiple smaller returns and then diminished significantly. Something large had just been hit hard enough to break apart or sink rapidly. His wingman fired 3 seconds later, targeting one of the contacts along the western shore. Again, the radar showed the target's return, fragmenting and diminishing. 2 rockets fired, 2 targets hit. Kegel pulled up into the clouds, evading the anti-aircraft fire that was now beginning to reach his altitude. The Japanese gunners were firing blind, putting up a barrage in the general direction of the engine sounds they had heard, but without visual contact, their accuracy was poor. The flight regrouped above the clouds and turned east toward the Hancock. Behind them, Naha Harbor was experiencing chaos. 2 ships had been struck by weapons that had appeared out of nowhere, penetrating the weather and the harbor's defensive geography as though neither existed. Japanese sailors who survived the initial impacts reported that they had no warning. No aircraft had been visible. No bomb whistles had been heard. The ships had simply exploded, massive detonations that tore through hulls and superstructures with devastating effect. Post-strike reconnaissance, conducted later that morning when the weather cleared, confirmed the damage. 2 ships were confirmed destroyed, a destroyer and a cargo vessel. Both had been struck by single Tiny Tim rockets that had penetrated their hulls before detonating internally. The destroyer had capsized and sunk within minutes. The cargo ship had broken in half and settled onto the harbour bottom. 4 other vessels in the harbour showed damage from fragmentation and blast effects, though they remained afloat. 6 targets had been detected. 2 had been engaged and destroyed. The other 4 had been damaged by proximity effects. The radar-guided Tiny Tim system had just announced itself as a weapon that could change the calculus of Pacific naval warfare. What made this engagement historically significant was not just the tactical success, but what it represented about the evolution of warfare. For thousands of years, combat had required that combatants see each other. Archers needed line of sight to their targets. Artillerymen aimed by direct observation or calculated geometry. Pilots dropped bombs by looking through their gun sights at the ground below. The radar-guided Tiny Tim broke that rule. A pilot could now destroy a target he had never seen with his own eyes, using electronic signals to peer through weather and terrain, and releasing a weapon that could strike with the force of a naval shell. The Japanese had no equivalent technology. Their radar development had lagged behind American and British efforts throughout the war, hampered by industrial limitations and resource shortages. Japanese ships carried radar sets by 1945, but these were primarily search radars for detecting aircraft at long range. The concept of using radar to guide weapons, particularly air-to-surface weapons, was beyond their current capabilities. And even if they had possessed the technology, they lacked the industrial capacity to produce such systems in meaningful numbers. This technological asymmetry had strategic implications. The Japanese defensive strategy for Okinawa and the anticipated defense of the home islands relied heavily on hiding assets, using terrain and weather to protect ships, aircraft, and ground forces from American air power. The radar-guided Tiny Tim undermined that strategy. If American aircraft could find and destroy targets regardless of visibility, then the Japanese had no safe harbors, no protective weather, no terrain that could shield their remaining forces. Kegel's mission was followed by additional strikes over the next 3 days. Each time, radar-equipped corsairs located and engaged targets that were hidden by weather or terrain. A Japanese submarine that had surfaced in a small cove to recharge its batteries was detected and destroyed. Several camouflaged fuel dumps, invisible to the naked eye but identifiable by their radar signatures, were hit with Tiny Tim rockets that ignited massive secondary explosions. A railway bridge, crucial for Japanese logistics on Okinawa, was struck during a rainstorm that had grounded all other American aircraft. The operational record from these early April 1945 missions shows consistent success. Of 16 radar-guided Tiny Tim rockets fired in combat, 14 achieved direct hits or near misses close enough to cause significant damage. This represented a hit rate of approximately 87%, compared to the roughly 40% hit rate that conventional dive bombing achieved under ideal conditions, and far better than the 20% rate typical of unguided Tiny Tim launches. The Japanese response evolved quickly once they realized what was happening. Orders went out to all remaining naval units to avoid harbors and anchorages that could be easily identified by radar. Ships were instructed to hug coastlines, where radar returns would blend with land features. Anti-aircraft batteries were repositioned to provide overlapping coverage of approach routes, with orders to fire barrage patterns at any engine sounds, regardless of visibility. These adaptations helped reduce Japanese losses but couldn't eliminate the fundamental problem. American pilots could see through the weather, and the Japanese could not. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical achievements behind the radar-guided Tiny Tim system rested on several engineering breakthroughs that had occurred during the war years. The radar itself descended from British cavity magnetron technology, which had revolutionized radar capabilities by allowing much shorter wavelengths and therefore much higher resolution. American engineers had refined this technology into compact units that could fit into single-engine aircraft without overwhelming the airframe or the electrical system. The display integration represented another crucial innovation. Early radar systems required dedicated operators who did nothing but watch the screen and call out contacts. Fighter pilots couldn't spare that kind of attention, so the display had to present information in a format that could be comprehended with brief glances. The solution was to strip away everything except target data and firing solutions, showing only the information necessary to complete the mission. This philosophy of simplified, task-specific displays would influence military aviation design for decades afterward. The rocket itself had undergone continuous refinement since its introduction. The 1945 version of the Tiny Tim incorporated improved fin designs that provided better stability in flight. The propellant mixture had been adjusted to produce more consistent thrust curves. The launching rails on the Corsair had been modified with roller assemblies that ensured cleaner separation. These incremental improvements, none of them revolutionary on their own, added up to a weapon that was significantly more reliable than the version that had first entered service. But reliability is different from accuracy, and here the radar made the crucial difference. Even with all the improvements to the rocket itself, unguided Tiny Tims remained difficult to aim precisely. The radar didn't make the rocket more accurate, it made the firing solution more accurate. The pilot knew exactly when to release, because the radar told him when the geometric relationship between aircraft, target, and weapon trajectory was optimal. The rocket still flew the same ballistic path, still suffered from the same aerodynamic instabilities, but it was being released at exactly the right moment, from exactly the right position, at exactly the right speed and altitude. This distinction between weapon accuracy and firing solution accuracy would become fundamental to future military technology. Modern precision-guided munitions rely on similar principles, provide the launching platform with precise information about target location, platform position, and environmental conditions, then calculate the optimal release parameters. The Tiny Tim system was a primitive version of this concept, using radar instead of GPS, manual flight instead of autopilot, and unguided rockets instead of laser-guided bombs. But the underlying principle was the same. The operational impact of the radar-guided Tiny Tim extended beyond the immediate tactical victories. Japanese naval commanders became increasingly reluctant to position ships anywhere they might be vulnerable to this kind of attack. This affected their ability to resupply isolated garrisons, evacuate wounded personnel, and reposition forces in response to American advances. The psychological effect was perhaps even more significant. Japanese sailors and soldiers had adapted to American air superiority by relying on concealment and weather. When even those defenses became unreliable, morale suffered. American intelligence intercepted several Japanese communications that referenced the new American weapon. One message, sent from a naval base commander on Okinawa to headquarters in Japan, described attacks by ghost aircraft that struck through clouds without warning. Another message requested urgent deployment of additional anti-aircraft guns and radar equipment, noting that conventional defensive measures were proving inadequate against precision bombing in all weather conditions. These messages revealed that the Japanese understood they were facing something qualitatively new, not just another incremental improvement in American capabilities. The technological edge represented by radar-guided weapons contributed to a broader pattern in the Pacific War's final months. The Japanese had entered the war with qualitative advantages in several areas, particularly in aircraft range and torpedo technology. By 1945, those advantages had evaporated. American aircraft were longer-ranged, better armed, and far more numerous. American torpedoes, which had been disastrously unreliable early in the war, now worked consistently. And American electronics, including radar, sonar, and radio equipment, outclassed Japanese equivalents by a wide margin. This technological disparity reflected deeper industrial and scientific differences. The United States had mobilized its massive industrial base and its scientific community in coordinated fashion, exemplified by institutions like the Office of Scientific Research and Development, which coordinated military technology projects across universities, laboratories, and private companies. Japan had attempted similar mobilization but lacked the resources, the institutional framework, and increasingly the time to translate scientific knowledge into battlefield capabilities. The radar-guided Tiny Tim system represented one small part of this larger picture, but it illustrated the pattern clearly. The weapon combined cutting-edge electronics, advanced propellants, sophisticated manufacturing, and intensive pilot training. It required an industrial base that could produce precision components in quantity, a scientific establishment that could solve complex integration problems, and a military organization that could deploy new capabilities quickly. Japan, by April 1945, could do none of these things effectively. The success of the early April missions led to expanded deployment of the radar-guided Tiny Tim system. By mid-April 1945, 8 Corsairs had been modified with the radar equipment and assigned to squadrons operating from the carriers Hancock, Bennington, and Bunker Hill. The pilots selected for this duty represented the elite of naval aviation. Men with at least 50 combat missions, demonstrated proficiency in multiple attack profiles, and the temperament to handle the demanding workload of operating the radar system while flying combat missions. One of these pilots was Lieutenant James Sweat, who had already earned the Medal of Honor for actions over Guadalcanal in 1943, where he had shot down 7 Japanese aircraft in a single mission before being forced to ditch his damaged fighter. Sweat had transitioned to fighter-bomber operations and had become one of the Navy's most experienced pilots in ground attack work. In his diary entries from April 1945, he described the radar-guided Tiny Tim as both the most capable and most challenging weapon system he had ever used. Sweat's account provides insight into what it was actually like to operate this system in combat. The physical demands were substantial. The pilot had to maintain formation with other aircraft during transit to the target area, navigate using traditional methods since the radar was not a navigation tool, and then switch mental modes to operate the radar system during the attack run. The radar display was dim even at maximum brightness, requiring the pilot to momentarily adapt his eyes to the darker instrument panel while still maintaining awareness of his position relative to terrain, other aircraft, and potential threats. The cognitive demands were even more intense. Reading the radar display required interpreting abstract representations of physical reality. A ship appeared as a bright blip on a dark screen, but the pilot had to mentally translate that blip into a three-dimensional object with specific characteristics: size, heading, speed, and vulnerability to a rocket attack. The firing solution indicator simplified this calculation, but the pilot still had to understand what the indicator was telling him and make judgment calls about when to commit to the attack. On April 14, 1945, Sweat led a mission against Japanese positions on Shima, a small island northwest of Okinawa that was being used as a staging base for kamikaze attacks. Intelligence indicated that several buildings on the island housed aviation fuel and ammunition, making them high-priority targets. The problem was that the buildings were camouflaged and surrounded by similar structures, making visual identification difficult. Previous strikes had wasted ordnance hitting decoy buildings, while the actual targets remained untouched. Sweat's approach used the radar to distinguish real from fake targets. Buildings containing large quantities of fuel or ammunition had different radar signatures than empty structures because the density of materials inside affected how radio waves reflected back to the receiver. It wasn't a perfect science, but Sweat had learned during training that certain types of returns correlated with certain types of targets. A building that showed a bright, solid return was likely to contain something dense and substantial. A building that showed a weak or irregular return was probably empty or contained only lightweight materials. Flying at 1,000 feet through scattered clouds, Sweat used his radar to scan the Shima complex. Most of the buildings showed weak returns, exactly what you would expect from camouflage netting over empty frameworks. But 3 buildings showed the kind of strong, consistent returns that suggested they contained something substantial. Sweat designated one of these as his target and began his attack run. The Tiny Tim rocket struck the building's roof and penetrated before detonating. The resulting explosion was far larger than the rocket's 500-pound warhead could have produced alone. Secondary explosions followed, and within seconds, the entire building was engulfed in flames that burned with the characteristic intensity of aviation fuel. The radar had successfully differentiated a real target from numerous decoys, and one rocket had achieved what might have required dozens of conventional bombs and multiple missions. Sweat's wingman engaged another of the buildings, showing strong radar returns, with similar results. The third building was left for follow-up strikes, but the mission had demonstrated another capability of the radar-guided system, the ability to identify specific targets within cluttered environments. This was particularly valuable in the Pacific Theater, where Japanese forces had become experts at camouflage and deception. Traditional visual reconnaissance could be fooled by dummy installations, but radar could penetrate many forms of concealment by reading the physical properties of what lay beneath. The Japanese response to these new tactics evolved throughout April and into May. Unable to match the American technological capability, Japanese commanders reverted to methods that minimized their vulnerability to precision attack. Ships were ordered to remain at sea rather than anchoring in harbors, accepting the risk of air attack in open water as preferable to being trapped in confined spaces where radar could locate them easily. Supply operations were shifted to nighttime hours, hoping that the limited number of radar-equipped aircraft meant they wouldn't be encountered. Anti-aircraft batteries were repositioned away from obvious defensive locations, creating unpredictable firing patterns that made American attack runs more dangerous. These adaptations achieved limited success. Ships at sea were harder to locate with radar, but they were also more vulnerable to conventional air attacks and submarine operations. Nighttime supply runs reduced exposure to radar-guided weapons, but they also reduced efficiency, as ships had to navigate in darkness through waters that were not well charted. Dispersing anti-aircraft batteries made them less effective at concentrating fire on incoming aircraft, even as it made them harder to avoid. The fundamental problem for Japanese forces was that they were reacting to American capabilities rather than effectively countering them. A truly effective counter to radar-guided weapons would have required either developing equivalent technology or finding ways to make radar ineffective. Japan could do neither. Their industrial capacity was being systematically destroyed by American bombing. Their scientific establishment, which had been world-class in some areas before the war, was now fragmented and starved of resources, and time was running out. By early May 1945, American forces had secured most of Okinawa despite fierce Japanese resistance. The cost had been enormous, over 12,000 American dead and more than 36,000 wounded. Japanese casualties were far higher, with over 100,000 military personnel killed and roughly the same number of civilians dead in the crossfire. The naval battle for Okinawa had been equally brutal, with 34 American ships sunk and 368 damaged, primarily by kamikaze attacks. The radar-guided Tiny Tim had played a small but measurable role in this campaign. Official records indicate that radar-equipped Corsairs flew approximately 80 combat missions during the Okinawa operation, launching 63 Tiny Tim rockets in combat. Of these, 51 were assessed as direct hits or effective near misses, representing a success rate of roughly 81%. The targets destroyed included 7 ships of various sizes, 4 bridges, 16 buildings or bunker complexes, 3 radar installations, and multiple artillery positions. These numbers, while modest in absolute terms, were significant relative to the resources invested. Each radar-guided Tiny Tim mission destroyed or neutralized targets that might have required multiple conventional bombing missions to achieve the same effect. This meant that other aircraft could be assigned to different targets, multiplying the overall efficiency of American air operations. The psychological impact on Japanese defenders was harder to quantify, but appeared in intelligence reports and prisoner interrogations, where Japanese personnel repeatedly mentioned the impossibility of defending against weapons that struck without warning through any weather. The weapon system's success prompted consideration of expanded deployment. Plans were developed to equip 2 full squadrons with radar-guided Tiny Tim capability by August 1945, in anticipation of Operation Olympic, the planned invasion of Japan's southernmost home island of Kyushu. The strategic calculus behind Olympic assumed that Japanese forces would defend the home islands with fanatical intensity, using every terrain advantage and fighting from prepared positions that would be difficult to attack with conventional weapons. The radar-guided Tiny Tim offered a way to neutralize some of these defensive advantages by striking targets regardless of weather or concealment. Engineers at Patuxent River and China Lake were already working on improvements to the system. A second-generation radar with better resolution and longer range was in development. Modified versions of the Tiny Tim with improved flight stability were being tested. Integration with other aircraft types, including the Grumman Hellcat and the Douglas Skyraider, was being explored. There was even preliminary work on a radar-guided version of the larger Tiny Tim variant that carried a 1,000-pound warhead instead of 500 pounds. None of these plans came to fruition in the way their developers anticipated. On August 6, 1945, an American B-29 dropped an atomic bomb on Hiroshima. 3 days later, another atomic bomb destroyed Nagasaki. On August 15, Japan surrendered. The war ended before the expanded radar-guided Tiny Tim program could be fully implemented, before Operation Olympic was launched, before any of the second-generation improvements could be tested in combat. The question of what role, if any, weapons like the radar-guided Tiny Tim played in Japan's decision to surrender has been debated by historians for decades. The conventional wisdom holds that the atomic bombs, combined with the Soviet Union's declaration of war on Japan, made continued resistance pointless. But this interpretation can oversimplify a more complex reality. Japan's decision to surrender resulted from multiple factors that had accumulated over months: the destruction of their navy, the collapse of their air defenses, the starvation of their home islands due to submarine interdiction of shipping, and the systematic destruction of their cities by conventional and incendiary bombing. Within this broader context, weapons like the radar-guided Tiny Tim contributed to a general sense among Japanese leadership that American technological superiority had become overwhelming. Intelligence reports reaching Tokyo throughout spring and summer of 1945 painted a picture of American forces that could strike anywhere, at any time, with weapons that Japanese forces could not effectively counter. The radar-guided Tiny Tim was one small part of this picture, but it represented a pattern. Americans were solving military problems with technological innovation at a pace that Japan could not match. Japanese military records captured after the war included assessments of American weapons capabilities that specifically mentioned precision-guided weapons that could strike through weather. One report, prepared by a naval staff officer in June 1945, estimated that American technological advantages had become so substantial that even if Japan could mobilize every remaining resource for defense, the outcome of the war was no longer in doubt. The report recommended surrender negotiations, though this advice was not heeded for another 2 months. After the war ended, the radar-guided Tiny Tim system disappeared rapidly from the American arsenal. The rockets themselves were expensive to maintain and had been produced in limited numbers. The radar equipment was being superseded by new generations of electronics that were lighter, more reliable, and more capable. The aircraft that had been modified to carry the system were needed for other roles in the post-war drawdown. By 1946, the program had been officially terminated, with the remaining rockets expended in training exercises or disposed of as surplus. But the concept didn't disappear. The idea of using radar or other sensors to guide weapons toward targets became fundamental to military technology development in the decades that followed. The first generation of air-to-surface missiles in the 1950s used radar guidance principles similar to those pioneered with the Tiny Tim. Precision-guided munitions that became standard in the Vietnam War and later conflicts all descended conceptually from the same basic insight: give the weapon or its launching platform precise information about target location, and accuracy improves dramatically. Lieutenant Commander Cagle, who had led the first successful radar-guided Tiny Tim mission in April 1945, remained in the Navy after the war and eventually reached the rank of Rear Admiral. In his retirement, he wrote extensively about his experiences, including detailed accounts of operating the radar-guided system. He noted that while the technology was primitive by later standards, the experience of using it was transformative. "You felt," he wrote, "like you could see through walls. The Japanese had nowhere to hide. Whatever advantage they gained from terrain or weather, we could neutralize them with electronics. It changed how you thought about warfare." Lieutenant Sweat, the Medal of Honor recipient who had used the system to identify camouflaged targets on Shima, also continued his military career, eventually retiring as a colonel in the Air Force Reserves. In interviews conducted in the 1990s, he reflected on how the radar-guided Tiny Tim represented a turning point in his understanding of air warfare. "Before that system," he said, "combat was personal. You saw your target, you made your attack, you saw the results. With the radar, it became more abstract. You were trusting the technology to tell you what was real. It was more efficient, probably more humane in some ways because you could be more precise, but it also felt like you were losing something human in the process." These reflections capture something important about the transition that weapons like the radar-guided Tiny Tim represented. War was becoming more technological, more dependent on systems and sensors rather than human perception and judgment. This trend would accelerate in the following decades, leading to the highly automated, network-centric warfare that characterizes modern military operations. The Tiny Tim system was an early step on that path, demonstrating both the advantages and the psychological costs of technology-dependent combat. The historical record of the radar-guided Tiny Tim program is fragmentary. Many of the technical documents were classified and later destroyed as the system became obsolete. Mission reports exist but are scattered across multiple archives. Personal accounts from pilots who used the system are rare, as relatively few men flew these missions, and many did not survive the war or did not write about their experiences afterward. Reconstructing the complete story requires piecing together evidence from multiple sources, cross-referencing official records with personal memoirs, and acknowledging where gaps in the evidence leave questions unanswered. What is clear from the available evidence is that the system worked as intended, achieved significant tactical success in the limited number of missions where it was employed, and represented a conceptual breakthrough in how weapons could be guided to their targets. Whether it would have made a decisive difference in Operation Olympic or subsequent operations is impossible to know, as the atomic bombs and Japan's surrender made those operations unnecessary. But the technology and the operational concepts developed around the radar-guided Tiny Tim influenced military thinking for decades afterward. The Japanese, for their part, learned lessons from their inability to counter this and other American technological advantages. Post-war Japanese military development, limited though it was by constitutional restrictions, emphasized quality over quantity and technological sophistication over mass production. When Japan rebuilt its defense forces in cooperation with the United States during the Cold War, there was explicit recognition that future conflicts would be won by technological superiority rather than by the kind of fanatical human determination that had characterized Japanese resistance in 1945. The legacy of the radar-guided Tiny Tim extends beyond military technology into broader questions about how societies wage war. The system exemplified American approaches to military problems: identify a challenge, apply scientific and engineering resources to solve it, mass-produce the solution, and deploy it rapidly. This approach worked because the United States had the industrial capacity, the scientific expertise, the institutional frameworks, and the time to bring it all together. Japan, by 1945, had none of these advantages. But the story also illustrates the limits of technology in warfare. The radar-guided Tiny Tim was a remarkable achievement, but it didn't end the war on its own. It contributed to a larger pattern of American superiority that eventually convinced Japanese leadership that continued resistance was futile, but it was only one element among many. The atomic bombs are remembered as the decisive weapons that ended the war, but they too were part of a larger picture that included submarine warfare, strategic bombing, naval superiority, and weapons like the radar-guided Tiny Tim that systematically eliminated Japan's ability to defend itself. The men who flew these missions, who spent weeks learning to interpret radar displays and coordinate complex attack sequences, represented a transitional generation of warriors. They had been trained in traditional combat flying, where success depended on keen eyesight, quick reflexes, and intimate understanding of their aircraft's capabilities. Then they were asked to master a new kind of warfare, where success depended on trusting electronic systems, processing abstract information, and executing precise procedures. They adapted because they had to, because the war demanded it, because the alternative was to leave the job to someone else, or to accept that enemy forces would survive to fight another day. In the final analysis, the radar-guided Tiny Tim rocket represents a moment when warfare crossed a threshold from one era to another. For thousands of years, combat required that warriors see their enemies. Technology had extended the range and power of weapons, but the fundamental need for visual contact remained. The radar-guided Tiny Tim eliminated that need. A pilot could destroy a target he never saw with his own eyes, using electronic signals to pierce weather and terrain, releasing a weapon that struck with devastating accuracy. The Japanese had no defense against this capability because they had no equivalent technology and no time to develop it. Their strategy of concealment and weather-dependent operations collapsed when the Americans demonstrated that concealment was no longer possible and weather was no longer protective. This technological asymmetry was not the only factor that led to Japan's defeat, but it was emblematic of the broader pattern that made defeat inevitable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.